Okay, AP Physics 1, we're going to continue our discussion of linear momentum by talking about one of the most important concepts in all of physics, the law of conservation of momentum. Before we talk about conservation of momentum, though, it would be kind of a good idea to go back and review how exactly we define Newton's laws of motion in terms of momentum. So as a brief reminder, when it comes to forces, Newton's first law of motion tells us if the forces on an object are balanced, the motion of the object remains constant. So by balanced, we mean there's no net force, there's no acceleration, the velocity is constant, so delta v is equal to 0. And in terms of momentum, really just a minor tweak. If the forces on an object are balanced, the momentum of an object remains constant. So rather than having v is constant, it's going to actually be p is constant, because p is simply equal to mv. So if there's no change in velocity, well, there's going to be no change in momentum too. And let's take it a step further with Newton's second law of motion. In terms of forces, that was if the forces on an object are unbalanced, if there is a net force, well then the object will accelerate. And it'll accelerate equal to the net force divided by the mass. Or a lot of times we write that as the net force is the mass times the acceleration. Well, in terms of momentum, if the forces of an object are unbalanced, well, then we say that the momentum will no longer be constant. It will, in fact, change. There will be an impulse, a change in momentum. And specifically, we can define the net force as equaling to the change in momentum over the change in time. But what about Newton's third law of motion? Can we redefine it in terms of momentum too? Well, let's go back a step. What is Newton's third law of motion? Well, it tells us that forces between objects occur in pairs, and that these forces in each pair are going to be equal in magnitude, opposite in direction, and they occur simultaneously. So if we look here, we say that the force of object 2 on object 1 will be equal to minus the force of object 1 on object 2. Well, going back to Newton's second law of motion, we can redefine the forces as being the change in momentum over the change in time. So because this is the force on object 1, this would be the change in momentum of object 1 over delta t1 equals minus delta p2 over delta t2. What is this delta t here again? Remember that that is the amount of time the force is being applied. Well, these force pairs occur simultaneously. If I push on one hand, well, the other hand is pushing back, and those occur over the exact same length of time. So delta t1 and delta t2, that's actually kind of the mislabel. We should really just say delta t. And we'll notice that now, well, we can say, oh, that's the same on both sides of the equation, so let's just get rid of it. And simplify this a little bit and be able to redefine Newton's third law in terms of momentum, ending up with delta p1 is equal to minus delta p2. So when we have two objects applying forces to each other, the change in momentum of one object is equal in magnitude and opposite in direction to the change in momentum of the other object. They both will have an impulse, but those impulses will be the same size but opposite in direction. So to see why this is so impactful, let's look at a little situation. Let's say we have two spheres, a red and a blue one. They both have the same mass. The blue one isn't moving, so its initial momentum is 0. The red one is moving with some speed v, so its momentum is the mass times the velocity, m times v. Well, you all probably have an idea of what might happen as soon as the red sphere impacts the blue sphere. In fact, if we do that, we see we get something like this, and we know for a fact that they're both going to apply a force to each other. And in fact, we probably can guess that the blue sphere is going to speed up and the red sphere is going to slow down. So in other words, the blue sphere is undergo a change in momentum, but Newton's third law in terms of momentum just told us that the red sphere is going to also undergo a change in momentum in the opposite direction that is the same size. And for the sake of this particular example, let's go ahead and say that delta p is actually equal to the momentum of the red sphere initially. So if the red sphere had momentum p and it underwent minus this change, we can go ahead and say, all right, well then the new momentum of this sphere will be 0, and the momentum of the blue sphere will be p. So we'll get something like this. And we notice a couple things here. If we look at two individual objects, originally the red sphere had momentum, the blue one did not. After they apply this force to each other, now we see the blue sphere has momentum and the red one does not. So momentum was literally transferred from one object to another. But additionally, if we treat both spheres like a single system, initially the momentum of the system was just the momentum of the red sphere, since the momentum of the blue sphere was 0. And afterward, if we look at the momentum of the system is also equal to p, because that's the momentum of the blue sphere, which equals that of the red sphere. So this momentum of the system is the same throughout, as momentum was transferred from one object to another. But we made a lot of assumptions there. Specifically, we said when they impacted each other, that each sphere would have a change of momentum equal to p, and well, that's not always going to be the case. If things hit each other, a lot of times this one will keep moving, and the other one will maybe not move quite as fast, etc. So we need somebody to explain every single situation. So let's go back to this formulation for Newton's third law in terms of momentum, that minus delta P1 is equal to delta P2. Well, how can we expand this to give us something a little more easier to understand in a lot of contexts? Well, let's start off by the fact looking at, well, okay, what is P? P is momentum, and momentum is mass times velocity, and delta P is typically m delta V, so I can substitute in for both of these. M1 delta V1 is equal to M2 delta V2. We have a minus sign on the left-hand side. And deltas are final minus initial. So I could take this a step further and expand it out and say I have minus M1 V1 minus V1 naught, remembering that 1 naught is telling us the initial velocity of this object, V1 is telling us the final velocity, is equal to M2 V2 minus V2 naught. Well, now let's distribute a bit, and so we're going to multiply those masses in. So I multiply M1 by both pieces, M2 by both pieces, and note, since this was negative, negative times a negative will give me a positive here. And at this point, let's rearrange a little bit. Don't really like negatives, so let's move this one over to the other side, and this one over to this side, so I get everything positive. And we actually see now I get M1 V1 naught plus M2 V2 naught is equal to M1 V1 plus M2 V2. But momentum is mv. So what this is really telling me is that the initial velocity of, the initial momentum of object 1 plus the initial momentum of object 2 will equal the final momentum of object 1 plus the final momentum of object 2. Or in other words, the momentum of the system, specifically the initial momentum of the system, will equal the final momentum of the system. So we've now mathematically derived that this should be the case in all circumstances. And this is a crucial law, which is why I put a bunch of little stars around it. This is the law of conservation of momentum, and it is one of the most foundational laws in nature. And it tells us that the total momentum of a closed system is constant. And specifically, if we write that in equation form, we would say P system naught is equal to P of the system. In other words, the momentum of the system before some sort of interaction should equal the momentum of the system after whatever this interaction is. It can a collision, an explosion, a force being applied, whatever, as long as the system is closed. And we'll talk about what that closed part means in a second. A couple of things here, though. First off, we say that it is constant because this is a conservation law, which is telling us that the total momentum will be conserved. It will be the same before, it will be the same after, it will be the same initial, same final. So that is what a conservation law is telling us. Now, how is that possible? If I have multiple objects, how can they consistently have the same total momentum? And that is because momentum is frequently going to be transferred from one object to another. It's not just spontaneously created or destroyed, and as long as it's a closed system, that momentum can just be transferred from one object to another. So let's look at an example to kind of see what we're talking about here. Let's say we have some frictionless surface and we have two blocks sliding towards each other, one being 0.5 kilograms, one being 1.5 kilograms, and the block on the left is moving 5 meters per second to the right, and the block on the right is moving 3 meters per second to the left. So this is at some time t naught. Well, eventually, these two blocks are going to impact each other. And when they do that, let's go ahead and say that we know a little bit of what it looks like afterward. And we know that the 1.5 kilogram block is now going to be moving at 0.5 meters per second to the left. But we don't know how fast the 0.5 kilogram block is going to be moving after this collision. And how exactly could we go about figuring that out? Well, first off, let's just kind of think through the situation. Now, knowing what even just using common sense, we can probably tell that the 0.5 kilogram block is going to be moving to the left. There's really no other way this makes sense. That if the right block, the 1.5 kilogram one, slows down but continues to move to the left, well, then the 0.5 kilogram one needs to move to the left too. Common sense is enough to give us that. Just our regular everyday experience is enough for us to expect that. But we don't have a specific number. And that is where we're going to have to, start looking at the conservation of momentum equation in a little bit more detail, because we want to know specifically how fast this object is going to move. Additionally, if we look, originally, this has some amount of momentum, this has some amount of momentum, and we can see that the momentum of the 1.5 kilogram block has decreased, so some of its momentum must have been transferred to the 0.5 kilogram block. Alright, so how can we go about doing this? Well, first, let's go ahead and identify all of our givens. I've just written out our masses and our initial velocities and the final ones. We don't know the final velocity of block 1, which I'm just calling the 0.5 kilogram. I'm calling block 2 the 1.5 kilogram. And you'll notice, though, I put minus signs on these two velocities because momentum is a vector. So it's very crucial that we go ahead and immediately define what is positive and what is negative. So I'm going to say positive in this situation is to the right, and I'm going to say negative is to the left. Alright, so we go ahead and write out the law of conservation of momentum. The initial momentum of the system will equal the final momentum of the system. And I've got two objects in my system. So I'm going to go ahead and break these both down into the respective objects. So the initial momentum of both blocks added together will equal the final momentum of both blocks added together. And momentum is mv, so now I'm going to take it a step further and say that p1 naught, for instance, is m1 v1 naught. I'm going to do that for all of the terms. And if we look, we actually already almost have everything given to us. Really, the only thing we're missing is this term, v1. So I'm going to go ahead and plug in all of my numbers. And when I do that, I would end up, take out your calculator, multiply these together, add that to this product. I would then subtract this piece over. And we're going to be getting, ultimately, if you do this in your calculator, we should be getting minus 1.25 is equal to 0.5 v1. That's just from doing all of the basic arithmetic and algebra there. So then we just divide by 0.5, and we get that v1 is minus 2.5 meters per second. So, one, it's a negative number, which makes sense because that means it's moving to the left, as we expected. And you might be thinking, well, how did it gain momentum? It was 5 meters per second, and now it's only going at 2.5 meters per second. But remember, its initial momentum, the 0.5 kilogram block, was to the right. And the 1.5 kilogram block gave it a lot of momentum to the left. And it transferred some of its momentum to it, causing it now to move to the left. Alright, so let's look at a slightly different situation that's going to take pretty much the exact same process. Let's say we have some dude with mass 60 kilograms running at some velocity 4 meters per second towards the skateboard. The skateboard has a mass of 5 kilograms. It's initially at rest. And we're going to say at some later time, the dude jumps on the skateboard, landing on it. And the question is, how fast are he and the skateboard moving together after he lands on it? Okay, so once again, let's go through all these details again. Let's go ahead and identify all of the givens we're given, which is the two masses of the dude. I did D for dude and SB for skateboard. The two masses and their initial velocities. And I went ahead and defined positive as the right. I'm going to say negative is the left. And we're going to use the law of conservation of momentum once again. So we have the initial momentum of the system has to equal the final momentum of the system. Well, what's our system? Well, it's going to be the dude and the skateboard, and initially we can treat them like two separate objects because they're not moving together. But at the end, we can treat them like a single object because they're moving in tandem. So we can combine them into a single object in the system. So in doing that, I go ahead and write out, okay, should actually say this is the initial momentum of the dude and the initial momentum of the skateboard equals the momentum of the system after the fact. And I go ahead and plug in mdvd naught plus msb vsb naught and the combination of the two afterward. And I'm going to go ahead and say, well, what am I looking for? I'm looking for this value here. Well, how can I find that? I literally just need to divide through by the mass of the two combined. So I'm going to go ahead and set that up. I'm going to get 60 times 4. The mass of the skateboard initially is 0, so I don't even need that. Divided by 65, and we solve and get an answer of 3.69 meters per second. And this makes sense, because initially, the dude is moving at 4 meters per second, but he transfers some of his momentum to the skateboard so that they can move together. And for that to occur, he will have to slow down. Now, conservation of momentum problems like the two we just saw are mathematically not really complicated. It's a lot of just multiplying, dividing, moving things across, a lot of basic arithmetic and basic algebra, but it's very, very easy to make some simple mistakes. So how can we go ahead and make sure that doesn't occur? One, if you don't have a picture, if it's not provided to you, it's highly recommended that you draw a picture of the system before whatever this interaction is and afterward to make sure you're not forgetting anything in particular and to make sure you're logically thinking through it. Second, we want to clearly define what is the positive direction and the negative direction, and we must be consistent with every piece. You mess that up, you're going to be in a lot of trouble. Third, we want to keep our variables clear. I think I have a typo here. There we go. We want to keep our variables clear. You've got multiple masses. You've got many different velocities, some initial, some final. It's very, very easy to mix some of those up. I pretty much just use different subscripts. However, if you want to go a step further and use different colored pens or pencils or highlighters or whatever to make sure you have every piece straight, this is really now the time to do it. And four, we want to define the system so that it is closed. But what exactly does that mean? Because we haven't really talked much about what a closed system is yet. So let's do that now. Well, going back to the law of conservation of momentum, it tells us that the total momentum of a closed system is constant. But what is a closed system? Well, ultimately, the most important idea here is that means there is no net external force. You can have external forces, but they have to be balanced. So the system cannot have any isolated external forces or anything that is unbalanced. Now, one quick thing I want to note is a lot of times you'll actually hear this called an isolated system rather than a closed system. It means the exact same thing. If you see that term, don't forget. Okay, so let's look at an example, really that's pretty much like our exact last problem, to understand what we mean by this. So when we look at our system here, at this problem, we want to define the system in a way that total momentum can be conserved. And let's say we're not sure how to do that. So let's kind of reason through it. Let's initially say, looking at the problem, okay, the dude goes and jumps on the skateboard. Let's say maybe the system is just the dude. You know, maybe that will work. Well, he initially has some momentum, but when he jumps on the skateboard, well, let's draw an FBD for him as he's jumping on the skateboard. Well, he's going to have a gravitational force down, a normal force up, but the skateboard, when he jumps on it, is going to apply a force of friction back to him. If it didn't, he would just slide right off the skateboard. And when that occurs, well, that is going to be a net external force on the system of the dude, causing him to slow down, causing his momentum to go down. So this is not a closed system, and the momentum of the system of just the dude is not conserved. Okay, well that wasn't right, so what about the skateboard? Maybe we could say that the system, the skateboard is a closed system. Well, initially its momentum is zero because it's not moving, and when he jumps on it, it starts moving. So we already see there might be a problem here because the momentum is definitely not constant. But why does that happen? Well, let's draw an FBD for the skateboard after he jumps on it, and we see that once again it has gravity and a normal force, but there's a force of friction from the dude on the skateboard, causing it to speed up. So once again, the system of just the skateboard is not closed, so the momentum can in fact not be conserved. Once again, this is not a situation. Just the skateboard is not enough for us to use the law of conservation of momentum. Alright, so you probably already have a guess on what we're going to go next. Let's say our system is both the dude and the skateboard. Alright, well, initially it has some momentum to the right because the skateboard's not moving. He's moving to the right. When he jumps on the skateboard, well, what are the forces on this system now? Well, we're going to have gravity going down and normal force from the earth going up on both him and the skateboard. But we're not going to have any friction forces here because the friction force he applies to the skateboard and it applies back, that's an internal force pair. So that is not an external force now because we've defined our system very carefully. So the system will now be closed and momentum will now be conserved. So we know for a fact that the momentum of this afterward must equal the momentum that it did beforehand. Being very careful and going through it, making sure that there's no external forces is very, very key. Now, what's an external force we probably would have expected in this situation would probably be friction from the ground on the skateboard. That when he jumps on it, there's going to be a net force from the ground causing it to slow down. So realistically, we really should have said that this was a frictionless surface in order to make sure that everything was working out okay. All right, let's do one practice problem all together, and I'm going to go ahead and introduce it, but then I think you should pause it, try it on your own, and see what you think. Let's say we have some astronaut out in space, and they're holding a fire extinguisher, and the astronaut and the fire extinguisher together have a mass of 90 kilograms, and they're initially at rest. And afterward, they spray the fire extinguisher. They, pull at the trigger on it and cause it to shoot out some compressed gas. And in fact, it shoots out 6 kilograms of compressed gas at a speed of 17 meters per second. And the question is, how fast does the astronaut and the fire extinguisher move in response to this? Like, how fast are they moving backward? We know for a fact that's going to occur. We did a situation like this when we talked about Newton's third law in terms of forces, but now we're going to look at it in this momentum framework. Now, just to be 100% clear, we know this must be a closed system, so momentum must be conserved because, well, what are the only forces? There's, as far as we can tell, no gravity, no air resistance. The only forces really are the fire extinguisher, the gases on the astronaut and the extinguisher, and the forces back. That's an internal force pair. We should be all good to go. Go ahead and pause. Give it a shot, come back, let's see how you do. All right, well, hopefully you gave it a try. So we're going to go ahead and say that the momentum of the system is conserved, and initially we can treat both the gases and the fire extinguisher and the astronaut like one single object, and that would be the initial momentum. So I really should put once again, initial there. And then afterward, we have that the gases can be treated like one object, and the astronaut can be treated like one object. And initially, the system had a momentum of 0, so we know that the final momentum of the system must add up to be 0. So this is mv for the astronaut, mv for the gases, and we just start plugging in numbers. Specifically, we're looking for v of the astronaut. So how could we find that? We could subtract this over and divide by the mass, and we go and plug in numbers: 6 kilograms, 17 meters per second, and 84 kilograms. This is probably where you made a mistake if you did not notice something very carefully, which is that the gases were contained in the fire extinguisher here. So there was 90 kilograms altogether. When you shoot 6 kilograms out, we have to remove 6 kilograms from what was the mass of the system. So now we are left only with 84 kilograms being the mass of the astronaut, the extinguisher, without the gases. Go ahead and plug that in our calculator, and we get negative 1.21 meters per second for this velocity, or 1.21 meters per second, we could say, to the left. Now, one thing I really want to quickly point out was that we could have already done this problem a couple of units ago. If we had known, for instance, like the size of the force between the two, we could have found the acceleration, we could have figured out some distances and some times and used a kinematic. But what's really useful about conservation of momentum is that in this situation, we avoided all that. I didn't need all that extra information. I didn't have to do all those extra steps because I could contain it all into this framework instead and go about it in a much simpler fashion. So learning when and when not to apply these sorts of frameworks is a very crucial way to basically make our work as easy as possible. Okay, so what are the takeaways for conservation of momentum? Well, 1, can we utilize the law of conservation of momentum to analyze the motion of objects before and after they interact when they're a part of some system? And can we define that system as being closed or not, making sure we're looking at is there a net external force on this system? And conceptually, can we connect the ideas of impulse and conservation of momentum? Now, the last point might sound a little confusing, but just remember that impulse is a change in momentum. How does conservation of momentum occur? Well, it's for a whole system, and that occurs when objects in the system transfer momentum to each other, changing their momentums and therefore undergoing equal and opposite impulses.